All right, hello everyone. Welcome to my channel. This is an educational channel. We look at great theories of everything, and some are ancient, some are modern. Today is our 508th video, 509th, sorry, 509th video that we've done on the reciprocal system of theory from Dewey Bernard Larson. And Mr. Larson lived in the 20th century, died in 1990. In 1959, he proposed his two fundamental postulates about how he believed the universe operated. And from there, he derived a theoretical universe, what his universe would look like if his postulates were correct. And then in many books, he compares his theoretical universe with the so-called actual or empirical universe of modern science. And we're looking at one of those books today, Basic Properties of Matter. This is mainly on chemistry. Larson comes up with equations from his postulates for many of the basic properties of matter. You know, things like the melting point, and then compares, plugs those into all of the elements and many compounds, and then compares them with the scientific tables already extant. And we are right in the middle of chapter 20, which is on magnetic quantities and units. Now, if you want to get a more detailed rundown of how the reciprocal system operates, fundamental postulates and his derivation, you want to watch any of my first 474 videos on this subject, where I get into that in a little bit more detail, 15, 20 or more minutes on that. But for the purposes of this video, I'm pretty much going to assume that you have a working knowledge of the reciprocal system, or are intrepid enough explorer into the world of the unknown that you are willing to just try to grab it by, the seat of your pants and just pick it up on the fly, which you can do. Larson may explain many of his key points here as he goes along in the discussion. Okay, so we're going to start right here. Larson just got done talking about magnetomotive force, and I guess just deriving those units here. So we will start right here. In our previous consideration of a magnetic quantity currently measured in amperes, the magnetic scalar potential, we found that the assigned dimensions are correct, but that the quantity has no physical significance. In the case of magnetomotive force, also measured in amperes in current practice, the magnetic quantity called by this name actually does exist in a physical sense, and it is a kind of force, but the dimensions currently assigned to it are wrong. As in the electric system, the magnetic field intensity is the potential gradient, and should therefore have the dimensions t squared over s to the third times 1 over s equals t squared over s to the fourth, the same dimensions that we found for the flux density. Just give you a hint if you are doing it by the seat of your pants here. T is time, s is space. Larson's universe is all of his units are in time and space only, and time and space are significant because they go into motion as reciprocals of one another, and that's how you get the reciprocal system of theory. And so all of his units are in time-space terms. And in this case, he's talking about magnetic field intensity, T squared over S to the fourth. The same dimensions we found for the flux density. The CGS unit, the Oersted, is 1 Gilbert per centimeter and therefore has the correct dimensions. However, the unit in the SI system is the ampere per meter, the space-time dimensions of which are... that was pretty loud lightning there. Hopefully that usually is enough to knock out the power here. So hang on tight. The space-time dimensions of which are S over T times 1 over S equals 1 over T. These dimensions have been derived from the ampere unit of magnetomotive force, and the error in the dimensions of that quantity is carried forward to the magnetic field intensity. Introducing the permeability corrects the dimensional error. Magnetic pole strength is a quantity defined as F over B, where F is the force that is exerted. Again, the permeability dimensions should be included. The correct definition is Pf over B, the space-time dimensions of which are T to the third over S to the fourth times T over S squared times S to the fourth over T squared equals T squared over S squared. Pole strength is thus merely another name for magnetic charge, as we might expect. The permeability issue also enters into the question as to the definition of magnetic moment. The quantity currently called by that name, or designated as the electromagnetic moment, symbol M, is defined by the experimentally established relation M equals NIA over A. I can't see. Yeah, NIA, where N and I have the same significance. Current, a number of turns and current, as in the related expression for magnetomotive force, and A is the area of the circuit formed by each turn of a coil. The space-time dimensions are S over T times S squared equals S to the third over T. The moment per unit volume, the magnetization, M, is S to the third over T times 1 over S to the third equals 1 over T. An alternate definition of the magnetic moment introduces the permeability. This quantity, which is called the magnetic dipole moment, to distinguish it from the moment defined in the preceding paragraph, has the composition MNIA. The space-time dimensions are T to the third over S to the fourth times S over T times S squared equals T squared over S. The distinction is not always effective, as some authors, Duffin for example, apply the dipole moment designation to the S to the third over T quantity. The dipole moment per unit volume, called the magnetic polarization, has the dimensions T squared over S to the fourth. This quantity is therefore dimensionally equivalent to the flux density and the magnetic field intensity, and is expressed in the same units. The question as to whether the permeability should be included in the moment affects other magnetic relations, particularly that between the flux density B and a quantity that has been given the symbol H. This is the quantity with the dimensions 1 over T that in the SI system is called the field intensity or field strength. Malcolm McCabe reports that the, quote, the name field for the vector H went out of fashion for a time, and says that he was asked by publishers to use magnetizing force instead. But quote, "The term magnetic field strength now seems to be in fashion again. The relation between B and H has supplied the fuel for some of the most active controversies in magnetic circles." McCaig discusses the controversial issues at length in an appendix to his book, Permanent Magnets in Theory and Practice. He points out that there are two theoretical systems that handle this relationship somewhat differently. Both systems have international approval, he says, but there are intolerant lobbies on both sides seeking to have the other system banned. The two are distinguished by their respective definitions of the torque of a magnet. The Kennelly system uses the magnetic dipole moment, T²/s, and expresses the torque as T equals mh. The Summerfield system uses the electromagnetic moment, S⁻⁻T, and expresses the torque as T equals mb. Torque is a product of force and distance, T/s² times S equals T/s. The space-time dimensions of the product mh are T²/s times 1/T equals T/s. The equation T equals mh is thus dimensionally correct. The space-time dimensions of the product mb are S⁻³ times T²/s⁴ equals T/s. So the equation T equals mb is likewise dimensionally correct. The only difference between the two is that in the Kennelly system, the permeability is included in M, whereas in the Summerfield system, it is included in B. This situation emphasizes the importance of a knowledge of the space-time dimensions of physical quantities, particularly in determining the nature of the connection between one quantity and another. A mathematically correct statement of a physical relation is not necessarily a true statement, because at least some of the terms of that relation must have physical dimensions. Otherwise, it would be merely a mathematical statement, not a physical statement. And if those dimensions are wrong, the statement itself is physically wrong, regardless of its mathematical accuracy. The dimensions constitute a description of the physical nature of the quantities to which they apply, and give the mathematical statement of each relation a physical meaning. As matters now stand, this is not recognized by everyone. McCaig, for example, indicates in his discussion that he holds an alternate view, in which the dimensions are seen as merely a reflection of the method of measurement of the quantities. He cites the case of force, which he says could have been defined on the basis of the gravitational equation rather than by Newton's second law, in which event the dimensions would be different. The truth is that we do not have this option because the dimensions are inherent in the physical relations. In any instance where two different derivations lead to different dimensions for a physical quantity, one of the derivations is necessarily wrong. The case cited by McCaig is a good example. The conventional dimensional interpretation of the gravitational equation is obviously incompatible with the accepted definition of force based on Newton's second law of motion. The force cannot be proportional to the second power of the mass, as required by the prevailing interpretation of the gravitational equation, and also proportional to the first power of the mass, as required by the second law. And it is evident that an interpretation of the force equation that conflicts with the definition of force is wrong. Furthermore, this equation, as interpreted, is an orphan. The physicists have not been able to reconcile it with physical theory in general, and have simply swept the problem under the rug by assigning dimensions to the gravitational constant. McCaig's comments about the dimensions of torque emphasize the need to bear in mind that a numerically consistent relation does not necessarily represent physical reality, even if it is also consistent dimensionally. Good mathematics is not necessarily good physics. The definition of torque is Fs, the product of force and the lever arm, a distance. The work of rotation is defined as the product of torque and the angle of displacement, theta. The work is thus Fs theta. But work is the product of a force and the distance through which the force acts. This distance in rotation is not theta, which is purely numerical, nor is it the lever arm, because the length of the lever arm is not the distance through which the force acts. The effective distance is s theta. Thus, the work is not Fs times theta, torque times angle, but F times s theta, force times distance. Torque is actually a force, and the lever arm belongs with the angular displacement, not with the force. Its numerical value has been moved to the force merely for convenience in calculation. Such transpositions do not affect the mathematical validity, but it should be understood that the modification or the modified relation does not represent physical reality, and physical conclusions drawn from it are not necessarily valid. Reduction of the dimensions of all physical quantities to space-time terms, an operation that is feasible in a universe where all physical entities and phenomena are manifestations of motion, not only clarifies the points discussed in the preceding pages, but also accomplishes a similar clarification of the physical situation in general. One point of importance in the present connection is that when the dimensions of the various quantities are thus expressed, it becomes possible to take advantage of the general dimensional relation between electricity and magnetism as an aid in determining the status of magnetic quantities. For instance, an examination in the light of this relation makes it evident that identification of the vector h as the magnetic field intensity is incorrect. The role of this quantity, h, in magnetic theory has been primarily that of a mathematical factor rather than an expression of an actual physical relation. As one textbook comments, the physical, quote, the physical significance of the vector h is obscure. This explains why there has been so much question as to what to call it. Thus, there has been no physical constraint on the assignment of dimensions to this quantity. The unit of h in the SI system is the ampere per meter, the dimensions of which are s over t times 1 over s equals 1 over t. It does not necessarily follow that there is any phenomenon in which h can be identified physically. In current flow, the quantity 1 over s appears as power. Whether the quantity 1 over t has a role of this kind in magnetism is not yet clear. In any event, h is not the magnetic field intensity and should be given another name. Some authors tacitly recognize this point by calling it simply the h vector. As noted earlier, the magnetic field intensity has the dimensions t squared over s to the fourth and is therefore equivalent to mh rather than to h. This relation is illustrated in the following comparison between electric and magnetic quantities. Field intensity or flux density. For electricity, we have E equals V over S equals T over S squared times 1 over S equals T over S to the third, potential per unit space. E equals R over T equals T squared over S to the third times 1 over T equals T over S to the third, resistance per unit time. And then with the magnetic, we have B equals A over S equals T squared over S to the third times 1 over S equals T squared over S to the fourth. Potential per unit space is magnetic potential per unit space is, I can't remember the name of this Greek letter, times H times M over T equals T to the third over S to the fourth times 1 over T equals T squared over S to the fourth. Permeability per unit time. Ordinarily, the electric field intensity is regarded as the potential per unit distance, the manner in which it normally enters into the static relations. As the tabulation indicates, it can alternately be regarded as the resistance per unit time, the expression that is appropriate for application to electric current phenomena. Similarly, the corresponding magnetic quantity B, or Greek letter H, can be regarded either as the magnetic potential per unit space or the permeability per unit time. A dimensional issue is also involved in the relation between magnetization, symbol M, and magnetic polarization, symbol P. Both are defined as magnetic moment per unit volume. The magnetic moment entering into magnetization is S to the third over T, and the dimensions of this quantity are therefore S to the third over T times 1 over S to the third equals 1 over T, making magnetization dimensionally equivalent to H. The magnetic moment entering into the polarization is the one that is generally called the magnetic dipole moment, dimensions T squared over S. The polarization is then T squared over S times 1 over S to the third equals T squared over S to the fourth. Magnetic polarization is thus dimensionally equivalent to field intensity B. To summarize the foregoing, we may say that there are two sets of these magnetic quantities that represent essentially the same phenomena and differ only in that one includes the permeability, T to the third over S to the fourth, while the other does not. The following tabulation compares the two sets of quantities. So we have magnetic moment, S to the third over T. Dipole moment is putting the permeability in there, T to the third over S to the fourth times T third to the S to the third over T equals T squared over S to the fourth. Magnetization, 1 over T. Polarization, putting in the permeability is T squared over S to the fourth. Vector H, 1 over T. Field intensity, putting in the permeability is T squared over S to the fourth. A point to be noted about these quantities is that the magnetic polarization is not the magnetic quantity corresponding to the electric polarization. The magnetic polarization is a magnetostatic quantity with dimensions T squared over S to the fourth, and its electric analog would be an electrostatic quantity with dimensions T over S to the third. This is what electric polarization would be on the basis of the conventional theory of storage of electric charge in capacitors. But as we saw in chapter 13, the capacitor stores electric current, not electric charge. It has therefore been found necessary to introduce a term with the dimensions S squared over T into the mathematical relations, eliminating the electrostatic quantities, that is, reducing coulombs T over S to coulombs S, which Larson went through in a previous chapter. But just to kind of maybe refresh you, electric current in Larson's system is uncharged electrons, whereas electric charge is charged electrons. And in Larson's system, everything is a kind of motion. An electric current is a rotating unit of space, that is an electron, a rotating unit of space through time, which is generally matter is made out of time, while an electric charge is a rotational vibration that can that an electric current or an electron can take an electric charge, but it does not have to. So it can take an electric charge, a rotational vibration, and then become static electricity. An electric charge can also be applied to other forms of matter, subatoms or atoms, and it doesn't have anything to do with an electron. It has to do with a rotational vibration. Okay, so Larson kind of, I think, botched his units there in chapter 15, although that we will go over that again at some point. But he ended up kind of declaring that there are two kinds of coulombs. One of them is related to static electricity and the other to current. So, or to the electron, the uncharged electron, as opposed to the charged electron. The need for this mathematical adjustment is a verification of our conclusion that the electrical storage process does not involve any polarization in the electrostatic sense. The magnetic quantities identified in the discussion in this chapter, the principal magnetic quantities, we may say, are listed in Table 31 with their space-time dimensions and their units in the SI system. The magnetic scalar potential has been omitted from the tabulation for the reasons previously given, together with a number of other quantities identified in the contemporary magnetic literature in connection with individual magnetic phenomena that we are not examining in this volume, or in connection with special mathematical techniques utilized in dealing with magnetism. The dimensionally incorrect SI units for MMF, magnetomotive force, and magnetic field intensity are likewise omitted. Okay, so in the table, he's got magnetic quantities, SI units and dimensions, dipole moment, the Weber, Weber times meter equals T squared over S, magnetic flux, the Weber T squared over S squared, pole strength is the Weber T squared over S squared, vector potential is the Weber per meter T squared over S to the third, magnetomotive force T squared over S to the third, flux density, the Tesla, T squared over S to the fourth, field intensity, T squared over S to the fourth, polarization, the Tesla, T squared over S to the fourth, inductance, the Henry, T squared over S to the third, permeability, the Henry per meter, T squared over S to the fourth, magnetization, the ampere per meter, 1 over T, vector H, the ampere per meter, 1 over T, magnetic moment, ampere times meter squared equals S to the third over T, reluctance, 1 over Henry equals S to the third over T to the third. There is a question as to how far we ought to go in attaching different names to quantities that have the same dimensions and are therefore essentially equivalent. It would appear that the primary criterion should be usefulness. It is undoubtedly useful to distinguish clearly between electric quantity space and extension space, but it is not so clear that it is true of the distinction between the various quantities with the dimensions T squared over S to the fourth. For example, the magnetic field intensity can be identified with these dimensions by analogy with the electric field intensity. Perhaps there is some justification for distinguishing it from magnetic polarization, which has the same dimensions. Whether this is also true of the other T squared over S to the fourth quantities, such as flux density and magnetic induction, is somewhat questionable. The mathematical treatment of magnetism has improved very substantially in recent years, and the number of dimensional inconsistencies of the kind discussed in the preceding pages is now relatively small compared to the situation that existed a few decades earlier. But the present-day theoretical treatment of magnetism tends to deal with the mathematical abstractions and to lose contact with physical reality. The conceptual understanding of magnetic phenomena therefore lags far behind the mathematical treatment, This is graphically illustrated in Table 32. The upper section of this tabulation shows the corresponding quantities in electric and magnetic circuits, according to a current textbook, with the space-time dimensions of such quantity as determined in the present investigation. The lower section shows the correct analogs, magnetic equals electric times S, T over S. And in the 3 cases where a magnetic analog actually exists, only 2 of the 7 identifications in the textbook are correct, and in both of these cases, the dimensions that are currently assigned to the magnetic quantity are wrong. As brought out in the preceding discussion, the permeability, which belongs in both the magnetomotive force and magnetic field intensity, is omitted from these quantities in the SI system. Okay, so then he looks at this table 32, which has all of the associations from the different textbooks. We're going to skip that and go when the dimensions of the various magnetic quantities are assigned in accordance with the specifications in the preceding pages. These quantities are all consistent with each other and with the previously defined quantities of the mechanical and electric systems. This eliminates the need for employing illegitimate artifices such as attaching dimensions to pure numbers. The numerical magnitudes of the existing valid magnetic relations have already been adjusted in previous practice to fit the observations and are not altered by the dimensional clarification. This dimensional clarification in the magnetic area completes the consolidation of the various systems of measurement into one comprehensive and consistent system in which all physical quantities and units can be expressed in terms that are reducible to space and time only. There are, of course, many specialized units that have not been considered in the pages of this and the preceding volume, such as the light year, the unit of distance, the electron volt, a unit of energy, the atmosphere, a unit of pressure, and so on. But the quantities measured in these units are the basic quantities or combinations thereof, and their units are specifically related to the units of space and time, both conceptually and mathematically. And that is the end of chapter 20 on magnetic quantities and units. Chapter 21 is called electromagnetism, and we will be starting up on that chapter tomorrow when you tune in, hopefully. Thanks for tuning in today, and have a great